So thanks everybody for staying on for our next presentation. Up next is Dr. Sachini Wickramasinghe. Yes. Sachini is a research fellow in CFM who specializes in civil composites, specifically focusing on thermoplastics and fiber-reinforced composites. She has a wealth of experience in advanced 3D printing techniques for innovative material solutions, which will be what her presentation focuses on today. So Sachini, I'll pass it over to you.
Yes, thank you, Molly. Thank you for the great introduction. Okay, let me find which screen I'm sharing. Yeah, I got the wrong one. Yep. Can you see my presentation?
We see the PowerPoint one. It's not the in slideshow view. There it is. Perfect.
Okay, good. Okay. Good morning, everyone. I'm hoping everyone can hear me clearly. So as Molly introduced, I'm Sachini. I'm a research fellow in Civil Composite Group. So this presentation is simply based on my recent review paper. So I've got some case studies and examples on 3D printed fiber-reinforced polymer composites in civil infrastructure. So to begin with, slides moving. Yep. Okay. I'm not going to explain what FRP composites are because I'm pretty sure everyone in this seminar already knows what FRP composites are. But to start the presentation, I have some examples for FRP composites, some applications that we're using in civil infrastructure. So fiber-reinforced polymer composites are considered a smart and sustainable choice for civil applications, mainly because they have a great high strength to weight ratio and corrosion resistance, and of course the long service life compared to steel or timber. So some of these examples, these reinforcing rebars, which are alternative to steel rebars in concrete. So unlike steel, FRP rebars, they don't corrode, which is critical, especially in coastal and marine structures where saltwater exposure is a problem. And then we have utility poles. Again, these FRP poles are lightweight, easy to transport, and resistant to moisture and termites, making them, again, ideal for rural electrification projects or in areas which are prone to storm conditions. And the next example is railway sleepers. Again, these FRP sleepers are more durable than timber ones. And unlike concrete, they are very lightweight. Again, very easy to transport, easy to install, especially if we are installing them in remote areas. And then the last example, wind turbine blades, which is a classic example where lightweight composites allow for larger blade spans, capturing more energy while reducing structural loading. Of course, there's many other number of examples where we are using FRP composites in civil applications, such as bridge decks made from FRP panels to reduce dead loads and extended service life. And then we have strengthening wraps for existing concrete columns or beams. And then marine and offshore structures, where, again, durability against saltwater is essential. So what makes these FRP particularly interesting is that it's not only about performance, it also supports sustainability by extending the service life of infrastructure by reducing the maintenance, and FRP lowers the overall carbon footprint in civil construction. So in this slide, I have listed some of the conventional FRP manufacturing processes. So pultrusion is one of the FRP techniques that we are mainly working on at UniSQ. So pultrusion is ideal for producing long, constant cross-section profiles like rebars, beams, or rods. And filament winding, which is great for pressure vessels, tanks, and pipes. And then we have compression molding, vacuum assisted resin infusion molding, which are common for larger panels. But the key issue in most of these techniques is all of these are very labor intensive, quite costly, and it's limited in design flexibility. So for instance, in pultruded beams, which are strong and lightweight, but the process is limited to producing straight, constant cross-section profiles. So if there's a complex geometry is required, that need to be assembled by multiple pultruded parts, which is again introducing additional joints. So that's where the additive manufacturing steps in. It offers freedom in design and reduced material wastage. So in this slide, I've summarized some of the benefits of 3D printing or additive manufacturing. So as we all know, 3D printing allows design freedom. We can build curves, hollow sections, lattice structures, and multi-material layers that are somewhat impossible with traditional methods. It also supports rapid prototyping. Design iterations can happen within days instead of weeks. And waste reduction is also significant. Instead of cutting away excess materials in 3D printing, we only deposit what's needed, except for the supporting structures. And this is particularly important when working with high value materials like, for example, carbon fibers or engineered thermoplastics, which are quite expensive. So while traditional FRP methods have their place, additive manufacturing offers an entirely new toolbox for civil engineers, not just civil engineers, for many engineering industries. So moving on, there are a number of different 3D printing techniques, which I'm not going to explain in this presentation. In here, I'm focusing on extrusion-based 3D printing, because among many of these 3D printing techniques, extrusion-based method is widely used in civil applications due to their ability to produce large-scale, structurally robust elements with high precision and design flexibility. So it can either use short fibers or continuous fibers. And for example, here I have shown three popular examples. So the first one is the SEED largest robotic arm 3D printer. And then I have the gantry printer, which was developed at the University of Maine, that can print up to 30 meters long, 10 meters wide, and 5 meters in height. And then finally, at the bottom, I have an image of the Prime 3D printer, again from SEED, that can print continuous fibre-reinforced polymers. And it can print up to 4 meters, 2 meters by 1.5 meter in dimension. So in the next section, I want to show some research and development in this area and show how this research can actually help in making 3D printing as a viable manufacturing method of FRP composites, especially for civil infrastructure. So this first example, this is an example of showing the potential of these 3D printed FRP composites as concrete reinforcement. So in this research conducted in 2024, they have used Nylon reinforced with continuous carbon fibers with only 41% fiber volume fraction. So they have developed two designs, one which is a grid and the other one which is a bars, as you can see on the top two images. And then from the table below, you can see that the comparison of 3D printed part reinforcement and traditional molding with thermoset polymer reinforcement parts. And the thermoset FRP composite parts contain 70% reinforcement, 70% fiber volume fraction. So even with that, these 3D printed grid structure has managed to withstand a higher peak load compared to the traditional reinforcement. So this is just one example, research example that shows the potential of using this as a concrete reinforcement. And then on this slide, I have another example. So this is another interesting research conducted to replace the current PET foam cores with a 3D printed corrugated structure. So they have developed 4 different corrugated designs. The core is 3D printed using short carbon fibers reinforced with nylon, which is onyx, the commercial name, and then you have one with continuous carbon fiber reinforcement. So again, the summarized results on the bar chart, it shows how the flexural stiffness and the energy absorption has significantly improved with these different design iterations and with the addition of continuous carbon fibers compared to the conventional foam cores. So it's compared to the conventional foam cores, you can see it's 2 times higher in short carbon fiber reinforced core and 4 times in the continuous carbon fiber reinforced core. So moving on to the next example. So this is another example where 3D printed FRP composite bars used in repairing beam to column joint. So these bars are 3D printed using PLA and 20% carbon fiber reinforcement. So they have managed to improve the load capacity of the joint by 51% and increase the ductility up to 206%. So all these research efforts, they simply indicate the potential of using 3D printed FRP composite in civil infrastructure as a viable solution. So the last section, I just wanted to show you some of the real world applications or some of the large scale applications of FRP composites, showing how the research is being translated into real world solutions. So this first one, is an example of 2 footbridges developed in Netherlands as a collaboration of engineering consulting group and again seed in as I mentioned in Netherlands. So most of these fiber reinforced 3D printed infrastructure applications, Netherlands is far ahead in most of these research, and they have already done some of these real world applications. So these 2 examples I've given here. The first image, it shows the footbridge 3D printed using PET reinforced with glass fibers. And it is a 6.5 meter long bridge, which is 3D printed as one single module. And the best thing is it's a recyclable footbridge. So you can cut it into scraps and reuse it to 3D print another bridge. So the second image, that is another pedestrian bridge connecting existing wooden banks developed by the same collaborative companies. And it was 3D printed using waste PETG reinforced with 30% glass fibers. And then moving on to another example. So this is another great example of using 3D printed FRP composites in bridge construction. And this was done by a Shanghai construction group with Polymaker, and they have used glass fiber reinforced with ASA, which has a really good weather resistance and anti-aging properties. And they actually have developed 3 different bridges, and 2 of them they have managed to finish within just uh, 30 days, and the other one in just 5 weeks. And again, both of them were 3D printed as a single module. And the biggest bridge they have developed so far is the Luyen Bridge. A part of it is shown in the last image. And that one, it was 3D printed in separate modules because it is 21 meters long. But the interesting part is it was developed within just 35 days. And this next example, so this is a quite old example, which is in 2013 and 2016, but this is a great example to show the beginning of using FRP composites in civil applications. This one, it's the canal housing, and they have used natural fibers with recycled plastic materials. So as it's mentioned in the slide, it's 80% bio-based hot melt developed by a German chemical company, Henkel. And then moving on to the next slide. So this is one of my favorites. So a great example developed by the University of Maine. This one is called BioHome 3D. So this is printed using simple PLA thermoplastic and wood fibers. So it's a 600 square foot house, which is fully recyclable and can be 3D printed within just 48 hours. So you can own a house within just 48 hours. And after enduring a year of extreme weather in Maine, where the temperature is ranging from minus 17 Celsius degrees to 41 Celsius degree, BioHome 3D has met all the sustainability, strength, and durability requirements for US building codes, and as well as the design requirements of the International Code Council Code. So and then, yep. Oh yeah, this is a quick video of 3D printing part of this house. Of course, it's a fast forward video. It's not this fast, but as I mentioned, they finished the whole thing in just 48 hours. And then moving on to my, that's not the last slide. So even though there are 3D printed FRP composites, a great viable option or solution for civil infrastructure, there are still some challenges that need to be addressed in 3D printing FRP composites. So the research conducted so far along with these the exemplary projects I've shown, it demonstrates that most of these challenges have already been tackled in using 3D printed FRP composites, but there are still some challenges like current 3D printed composites. They often exhibit anisotropic properties, and then the polymers typically have lower durability under varying environmental conditions. And of course, one of the most important ones is the fire resistant, which is another critical concern. And the scalability of 3D printing technology remains as another barrier. Uh, so sorry, did I jump? Yeah. So just to conclude the presentation, in this last slide, I have highlighted some opportunities for using 3D printed FRP composites. Given that the construction industry is often associated with wasteful practices, 3D printing, 3D printed FRP composites could actually offer a much safer, much faster, and more cost-effective solution. So, as I said, currently construction is notorious for its wasteful practices. So 3D printing is a great alternative, especially when you're printing residential buildings. They would be so much cheaper and faster than using traditional methods, and it would greatly improve the housing affordability. And another great example is that this would be ideal for aiding reconstruction after natural disasters like earthquakes and floods. So, and that is actually the end of my presentation. Uh, so yeah, that's the link to my review paper. If you want to read more into this, that the paper got more content, and I've tried my best to summarize all the interesting parts. And thank you for listening.